Hello, this is chapter 4.3, and in this lecture we're going to be looking at the conformation of alkanes and cycloalkanes. There will be 4 videos in this particular lecture. The first one, which is this one, looks at conformational isomerism and the representations of molecules when talking about this topic. The second and third are a conformational analysis of ethane and butane respectively. And then the last video is a video concerning cycloalkanes and their isomerism, with a particular focus on cyclohexane. Let's have a quick recap concerning isomers. So these are compounds with the same molecular formulae but are structurally different in some way. So it's going to be important to recognize isomers because they have different chemical and/or physical properties, but potentially also different biological properties also. Now, constitutional isomers we met before, and these are the ones that have atoms connected in different ways. So these might contain different functional groups and or bonding patterns. For example, maybe they are branched. The other type of isomerism includes stereoisomers, and we've already seen cis and trans isomers as a form of diastereoisomerism for alkenes. This second type of diastereoisomerism are conformational isomers, also called rotamers, and these are not really thought of as being isomers because they are produced by the rotation or twisting about a sigma bond, and these are often rapidly interconverting at room temperature. So it's a little bit of a misnomer, but they have got energy differences. Once you start to cool these molecules down, they will adopt one conformation over another one. Here we see the rotation around a sigma bond in an ethane molecule. I've coloured the hydrogens in different colours so that you can see their positions relative to each other. We need to be able to represent this though in 2 dimensions. Let's have a look at some of these representations on the next slide. Here are 3 different representations of a conformational isomer or a rotamer of ethane. The first is a conventional representation in that we're looking at a side-on view of the carbon-carbon bond. 2 of the hydrogens are within the plane of your screen. 2 of the hydrogens, as indicated by the solid wedge, are coming out of your screen, and 2 of the hydrogens are going into the screen away from us. If we take the right hand carbon and rotate that towards us, then we start to get something called a sawhorse projection, and I've included a sawhorse at the right here just for your reference. The sawhorse is used by carpenters, and there are often 2 of them to provide a stable platform on which you would rest a piece of wood, and you would then cut that piece of wood or saw it. Now the third representation is brought about by continuing to rotate that right hand carbon towards us until we have a head-on view of this molecule, and we're looking down the carbon-carbon sigma bond. This is known as a Newman projection. I've included the ball and stick representation here to show that the hydrogen atoms completely occlude each other, unlike the 2-dimensional representation whereby we slightly offset this. You're going to need to be able to comfortably draw such isomers and representations, so let's see how this is done. So how do we draw a Newman projection from a conventional representation? Well, the first thing I'm going to encourage you to do in the early days of doing this is to build the model as seen on the left. You'll also need to reflect that the carbon framework has the methyl group on the left pointing down, and that it has the OH group pointing up. We try to put as many of the carbon atoms within the same plane as possible, and that's what gives that zigzag appearance as highlighted here. Now we're looking actually down the 2-1 bond, but just for convenience we've put 1 on the left and 2 on the right. The eye tells you that you're looking down this particular bond, so therefore you have to imagine that you're standing there, or you can rotate the molecule such that the methyl group is pointing down. Now when you start to do this, you'll notice that the chlorine, it should be on the right, and the hydrogen should then be on the left. So the solid wedges are on the right and the dashed wedges are on the left. So when we're drawing the Newman projection, note that the methyl group on the front carbon is pointed down, the hydrogen is on the left, the chlorine is on the right. The back carbon is the opposite. We have the OH group pointing up, but we still have the bromine, because it's a dashed group, on the left and the hydrogen of carbon 2 on the right. Don't worry, you're going to get some practice at doing this for yourself. You're also going to need to be able to convert between Newman projections and bond line structures. So here's an opportunity for you to do that. Please try and build this molecule and follow along as best as you can with this particular diagram. The idea is that the methyl group on the front carbon will be pointing up, the OH group will be pointing to the left, and the ethyl group will be pointing to the right. On your back carbon, these should be staggered by a methyl group to the left, a bromine group to the right, and the chlorine should be pointing down. Now when you rotate the molecule, this is the front carbon away from you, and you imagine where the man is standing, then you can start to apply the stereo bonds. So the OH group will be pointing away from you, the ethyl group will be pointing towards you, and the methyl group will still be pointing up. So we can use the stereo bonds as indicated on the diagram, and the same can be done for the back carbon. So my suggestion would be build models whilst you're doing this process, as it will help you visualize it in your head.
Concludes part A.
In this video we're going to have a look at the conformational analysis of ethane. But before we do this, we'll need to get some key terminology in place. One of the first things that we'll need to talk about is the dihedral angle. Now, when we look at ethane on the left, as shown by the ball and stick model, is in an eclipsed conformation. This means that each of the hydrogen atoms eclipses each other. But as we start to rotate the front carbon, then we'll need to keep a track of that relative to the back carbon. And what we use is something called the dihedral angle. The dihedral angle is defined as the angle between planes through two sets of free atoms that have two atoms in common. So our two sets of free atoms would include a carbon and two hydrogens, and the dihedral angles are typically 60-degree turns. If these 60-degree turns are made continuously, let's have a look and see how this affects the energy differences between these two types of conformation. Here is an energy profile that shows those successive 60-degree rotations of the front carbon of ethane. Now I've coloured the front hydrogen blue and the back hydrogen red so that you can keep a track of these rotations. As we can see, there are only two conformations, and they have either a high energy conformation or a stable low energy conformation. In fact, the difference between these two energy conformations is 12 kilojoules per mole. With respect to the eclipsed conformation, the first one, remember this looks like this, but we offset the atoms slightly. So hopefully this picture is a little clearer. Let's now define a reason for the difference in these energies. One of the reasons for the difference in energy is caused by this concept known as torsional strain. So if we think about this, we have electrons in electron clouds. So in our sigma bonds between our carbon and hydrogen atoms, these take up space. And so there will be some electron cloud repulsion. And forcing these atoms into this type of conformation is a large cost in energy. So we can think of these charges like magnets even, that they are like charges and so they want to repel each other and be away from each other. Each eclipsed conformation is higher in energy by 12 kilojoules per mole. And so that means then that each hydrogen that eclipses another hydrogen must contribute 4 kilojoules per mole, seeing as there are 3 eclipsed sets of hydrogen atoms. So 4 times 3 is equal to 12. Let's now take a look at the more stable conformation and what that's called. The other much more stable conformation is known as a staggered conformation, and this places all of those electron clouds as far away from each other as possible. This lowers the energy by 12 kilojoules per mole. So we've learnt that there are 2 conformations and that a staggered conformation is more stable than an eclipsed conformation.
This concludes part B.
Going to be looking at the conformational analysis of butane. In butane, it's possible to rotate 3 different carbon-carbon sigma bonds, either the 1,2 bond, the 2,3 bond, or the 3,4 bond. Now, the 1,2 and the 3,4 would give us the same energy profile. However, when you rotate around the 2,3 bond, this gives us a much more interesting energy profile, as we're able to see the interaction of 2 methyl groups. Let's go ahead and see what will happen when we rotate the front carbon 60 degrees, just like before. Ethane only provided us with 2 conformations. That was a staggered and an eclipsed conformation. However, this time we have a much more interesting energy profile. There are now 4 different conformations, and there are accordingly 4 different energies. So we have a 16 kilojoules per mole, a 0 kilojoules per mole, 4 and 19. So let's now take a look at the reasons behind these particular conformations and their relative energies. One thing you should note from this diagram is that all of the eclipsed conformations are at a much higher energy than any of the staggered conformations. For an eclipsed conformation, we see an additional type of strain. This is called steric strain, and the main differences between this type of strain and torsional strain are as follows. So steric strain is the repulsion between 2 atoms or group of atoms when the distance between them is decreased. Now, in order to see this on this molecule, I've provided both the ball and stick and also the space filling model as well. The space filling model shows what happens when the hydrogen atoms of the methyl group are brought into close proximity, and this is what we refer to as steric strain. This can't be lessened by rotating the molecule around a sigma bond, whereas torsional strain can be lessened by rotating the molecule around the sigma bond. Torsional strain occurs only when bond electrons pass by each other as the molecule is rotating. But steric strain occurs when the distance between the bulky groups of a molecule is decreased. So in this eclipsed conformation, so that's the 2 that are highlighted in the energy scheme, we see that this attributes an additional 11 kilojoules per mole of energy out of the 19 kilojoules per mole. So let's have a look on the next slide to see where the other forms of strain are occurring. We saw that on the energy profile, not all of the eclipsed conformations have the same energy, and so therefore to differentiate between the types of eclipsed conformation, we use the phrase syn periplanar. Syn refers to the fact that both of the methyl groups are on the same side with respect to the carbon-carbon single bond, that's the 2,3 bond. Periplanar refers to the 2 atoms or groups of atoms in a conformation that are in a single plane arrangement here. With respect to the strain, all of the steric strain is between the 2 bulky methyl groups, and an additional torsional strain is between the 2 hydrogen atoms as they rotate. So there are two sets of hydrogen atoms here. So this would actually contribute 8 kilojoules per mole and the steric strain 11 kilojoules. Hence this is what adds up to that 19 kilojoules and is the highest energy conformation for butane. Let's now take a look at some other named conformations as well. Here we see the other end of the spectrum, whereby this conformer has the lowest strain, that is no strain whatsoever. All of the atoms and groups are placed at a maximal distance to each other. So this has 0 steric strain and 0 torsional strain. This is the most important conformer. We call this an anti-periplanar arrangement of the atoms. Periplanar because, again, all of those groups are in the same plane, but anti because the two methyl groups are on opposite sides of the carbon 2-3 bond. Let's now take a look at some more conformers from that particular energy profile. Here we see the next two highest energy conformers. These are called anticlinal conformers, and the reason they're so called is because, again, the anti refers to the methyl groups being on opposite side of the carbon 2-3 bond, but the use of the phrase clinal refers to the idea that they have a torsional angle of between plus 90 to 150 degrees or minus 150 to minus 90 degrees. Anyway, the torsional strain and the steric strain combined is what adds up to that 16 kilojoules of energy. So there are two steric interactions between a methyl group and a hydrogen, and there are also the interactions between two hydrogens eclipsing each other. So we have two lots of steric strain, so that's 12, plus one lot of torsional strain is 4, gives you 16. So let's take a look at some more conformations on the next slide. Just as we looked at the two next highest conformers, that was the anticlinal conformers, we're now going to look at the next two lowest energy conformers. These are the synclinal, or otherwise known as gauche conformers. These are the staggered conformers, where you have two methyl groups that are still in some degree of proximity to each other. Now, the new kind of staggered conformation doesn't have any overlap, so there's no torsional strain, there is only steric strain. So we can see this when I put the electron clouds on here. And this is owing to the fact that the two groups are close enough, and these objects don't like being so close, so they repel one another. The most important conformers are the two extremes. That's the anti-periplanar, which is a staggered conformation. This has no torsional strain, no steric strain, and therefore is the lowest in energy, and also the highest in energy, which is the syn-periplanar conformer. This is the one that has the two methyl groups eclipsing each other.
This concludes part C.
And in this video we're going to pay particular attention to the conformations of cycloalkanes. To begin our discussion, we're going to look at the smallest possible cycloalkane. This is cyclopropane. Now, some of the torsional strain comes from the rotation of these bonds with respect to each other. And this only amounts to 24 kilojoules per mole. So with each hydrogen here that is eclipsing each other, this will cause that 4 kilojoules per mole. So that's 12 on the top and 12 on the bottom. But the rest of the strain comes from something called ring strain. And we can look at on the next slide how the size of the ring can affect the degree of ring strain. Let's take a look at this now. Here we see a graph of ring strain versus ring size. Now, cyclopropane has a very high degree of ring strain. It's almost 120 kilojoules per mole. But as the number of carbons in the ring increases, so from 3 to 4, the ring strain is reduced. and then as we go from 4 to 5, the ring strain is reduced even more, and then from 5 to 6, we end up with cyclohexane. And as you can see from here, cyclohexane has no ring strain. So this then increases again when we go to cycloheptane, and then increases again as we go to cyclooctane. Now, what is the reason behind the source of this ring strain? Let's take a look now. Ring strain occurs because the carbons in cycloalkanes are sp3 hybridized, which means they should have an ideal bond angle of 109.5 degrees. When they don't have that ideal bond angle, this causes an increase in the potential energy because of the desire for the carbons to be at that ideal bond angle. So for cyclopropane, we can see that the measured bond angles are 60 degrees. This is a 49 degree deviation from the ideal bond angle, and so therefore this causes considerable ring strain. When we move from a 3-membered ring to a 4-membered ring, this is cyclobutane, then there's now only a 19 degree deviation from the ideal bond angle, but even this is still quite high. And likewise for cyclopentane, even that 1 degree bond angle difference causes some degree of ring strain. It's only cyclohexane that doesn't experience this particular ring strain. Cyclohexane, when drawn as a 2-dimensional representation, can appear a little misleading. You might be tempted to think that this is flat. It really isn't. The conformation of a cyclohexane ring actually looks like a recliner, and this is the chair conformation. It's the most important of the cyclohexane conformers as it's the most stable. And the reason it's the most stable is because it doesn't have any torsional strain, and nor does it have any of that angular strain. Both of these are contributing factors to the concept we discussed on the previous slide, ring strain. Here are 3 different representations of a cyclohexane. The first one shows all of the hydrogens on the ring and shows their relative positions in space. The second shows a Newman projection that you can draw for a cyclohexane ring, and the last one just shows the carbon framework of the cyclohexane ring in a chair conformation. Let's take a look at the substituents on the ring and their names depending on their orientation. My advice to you while going through this video is to build yourself a cyclohexane ring, and when we're referring to these things you'll find it easier to have that visual cue. For substituents that stick out away from the ring, these are as far from anything as they can possibly be, and we describe these as being in an equatorial position. Notice that 3 of these equatorial R groups can be pointing up, and conversely 3 of the equatorial R groups can be pointing down. The other type of position is known as an axial position, and these substituents R groups are vertical. They are above and below the ring. Just like before, there are 3 pointing up and 3 pointing down. They are still quite close to each other, and this is important as we'll see in later slides. Cyclohexane can undergo a conformational change known as a ring flip. Here we see carbon 1 is puckered down, and what happens is that the other carbon at the end, which is carbon 4, when that becomes puckered down, this produces a boat, and the boat conformation is more strained because there is a steric hindrance between the hydrogens at the bow and the stern of this boat, as the other side is then puckered up to produce the other chair conformation. Notice what's happened to the axial hydrogens on 1, 3 and 5. These have all now become equatorial, and they have identical energies, these conformations, because hydrogen is the same size. However, if we have different substituents, as we'll see in later slides, this will affect the stability of those chair conformations relative to each other. The same process is shown directly underneath, but using a Newman projection. That is the only difference between these two sets of diagrams. In the next diagram, we see the relative energies of the cyclohexane chair and boat conformations. Please note that this is an abridged ring flipped, and there are other transitionary conformations that we have ignored. Here's a simplified diagram for the cyclohexane ring flip. We're only really interested in the two chair conformations and the one in the middle. The other energy maxima result from either a twist or a half conformation, and so I'm not really going to consider these any further. The difference in energy, however, between the chair and the boat is about 29 kilojoules per mole. Let's have a look at that boat conformation just in a little bit more detail. We can see from the space filling diagram of the boat conformation that the hydrogens at the stern and the bow are being brought into close proximity, and so this causes steric strain. However, there's also torsional strain, and this torsional strain is 29 kilojoules per mole, different to that of the chair conformation. And this is easily seen when you look at the Newman projection as the hydrogen atoms are eclipsing each other. On the next slide, we're going to then think about where do we place the substituents on our cyclohexane ring. You will need some practice in drawing cyclohexane, and I feel it best to leave it to you how to learn to do this. I provided a template showing the carbon skeleton. I would recommend that you practice drawing this. Here we see two different ways of drawing the cyclohexane chair ring flip process. My recommendation to you for drawing these is that you pick either the top or the bottom way of doing this and then be consistent in your approach. If you start off with a carbon puckered up, as demonstrated here, then in the corresponding chair conformer, that carbon must be then puckered down, or vice versa. So there will be lots of instructional videos that tell you how to do this, but they all will involve some use of parallel lines. Next, we're going to consider the placement of the substituents. The axial substituents are alternating vertical lines, so the carbon that is puckered down must have a downwards vertical line, and then these alternate up, down, up, down, up, down. Now, the really frustrating part about this is that if you don't do it this way, this means that the carbon does not appear like a tetrahedron, and it should. It is a tetrahedral carbon after all, and we've spent so much time talking about this fact. Please also don't use stereo bonds when drawing any of your bonds on the conformers. This is not the correct use of a stereo bond. The bolden lines are just here to represent that we've got 3 pointing up and then 3 pointing down for the lower carbons. All of the equatorial substituents all stick outwards and will be parallel. So guess what? That means parallel to the carbon-carbon framework, and this is indicated here. Just like before, we have this alternating pattern of up, down, up, down, up, down, and up, down. Let's now think about drawing these substituents onto our cyclohexane ring and thinking about the relative energies of these substituents compared with one another. When cyclohexane is substituted with one substituent, that substituent will always try to go for the equatorial position, and the reason is that it is more stable. So 95% of the time the methyl group in this case will be in the equatorial position, and 5% of the time it will be in the axial position. Let's take a look at a space filling diagram to see why this is so. Here we can see the two different chair conformations again with their equivalent space filling models. In the first instance, the methyl group is occupying the equatorial position and so sticks into space, which is away from the ring. But in the second instance, that methyl group is in an axial position, and as a result, one of its hydrogens is brought into close proximity to the hydrogens on carbons 1 and 3. We refer to these as 1,3 diaxial interactions, and these are examples of steric interactions that we want to avoid at all costs. To really bring this point home, I'm showing you what happens when we have a super big substituent like this tert-butyl group. Now the equatorial is 100% favoured, and the ring flip process is stopped because placing a tert-butyl group in an axial position would cause such unfavourable 1,3 diaxial interactions that in fact the ring flip for this does not happen at all. Let's now take a look at some di-substituted examples, and here we have a 1-2 relationship between two methyl substituents. We use the phrase cis when the two methyl groups are both pointing in the same direction. Here the stereo bonds indicate that these are pointing in an upward direction. Now, irrespective of ring flip, what's always going to happen is that you'll have one in an axial and one in an equatorial position. So as a result of this, both of these are the same in terms of their energy, and so there's no difference in equilibrium. However, if we look at the trans isomer, whereby we have one up and one down, if these were placed in an axial position, then this would be disfavoured because you'd have two sets of 1,3 diaxial interactions, those above the ring and also those below the ring. Therefore this is very unlikely to happen, and so most of the time the 1-2 relationship between these will be in an equatorial position, but note still that they have an up and down relationship as according to their stereo bonds. Cis 1,3 dimethyl cyclohexane has two methyl groups pointing downwards. These can either be in an axial position, as seen here, however this would be most unfavourable due to the 1,3 diaxial interactions. The most likely conformer is the one shown with the larger equilibrium arrow on the right hand side, whereby the two methyl substituents will be placed in an equatorial position. The other 1,3 dimethyl cyclohexane isomer is the trans isomer, and this time round, again, like the 1-2 example, if one is in an axial position and the other is in an equatorial position, then a ring flip is going to just have the same thing, one in an axial, one in an equatorial. Therefore this will have an equal distribution of these two conformers.
This concludes part D.